Hi, welcome to the Olympiad geometry. Let's continue our study on geometry theorem. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. So before we talk about the conjugate median, we need to still talk about another topic. That's Miguel's theorem. Let's see. In this video, we will talk about the mixed theorem, and also we will talk about the generalization of it. So let's look at the first theorem. It's called the three-circle theorem. Let three circles C1, C2, C3 concurrent on point O. M and P are the other intersection point of circle C1 circle C2, circle C2 and circle C3, circle C3 and circle C1 respectively. So let's just draw the figure first here. Let's call this one C1. This is another circle C2, and this point, let's call it O. So this is a third circle, let's call it C3. This point is O, and this point M. And that's C1, C2 intersection point, and C2, C3. So this one is N, this one is P, right? And let A be a point on circle C1. So let's just choose A to be here. A is a point on circle C1. Line MA intersects the circle C2 on B. So if we connect A and M and extend it, meet the circle C2 on this point B. Line PA intersects the circle C3 on C. So this point is C. Then B, N, C, these 3 points are collinear. Okay, B, N, C, these 3 points are collinear. So to prove this theorem, we just need to connect PO, connect MO, and connect ON, and connect NB, and then connect CN. Okay, so if we want to prove that B and C are collinear, we just need to B and C, these 3 points are collinear. The equivalent to the angle ONB plus angle ONC equals to 180 degrees, right? And we already know that angle ONB plus angle OMB equals to 180 degrees because OMBN is a cyclic quadrilateral, right? So this angle, the angle ONB plus angle OMB, that's 180 degrees, and we know that angle OMB equals to this angle equals to this angle, right? The angle OPA. Which also equals to angle CNO or angle ONC. Right? That means angle ONB plus angle ONC equals to 180 degrees, which means B and C are collinear. Okay, that's a three-circle theorem. And let's see the converse theorem. That's what we usually call Miguel's theorem. It seems that if M and P are 3 points on the edge of AB, BC, CA in triangle ABC. Okay, so let's we first have a triangle ABC here. M, N, P. Okay, M and P are the points on the edge A, B, B, C, C, A respectively. Then the circumcircles of triangle AMP, this triangle, and the triangle BMN, this triangle, and the triangle CPN, this triangle, are concurrent. It's basically saying that we have the circumcircle of triangle AMP here, and we have the circumcircle of triangle MBN here, right? And we will have circumcircle of triangle CPN, and we want to prove that this intersection point of the circumcircle of triangle AMP and circumcircle of triangle BMN would be on the circumcircle of triangle CPN, right? Which means we just need to prove that this point, let's call it O here. We just need to prove that OPNC is a cyclic quadrilateral, right? And we can simply connect OM here, because we already know that OPAM is a cyclic quadrilateral. So that means we know angle CPO equals to angle AMO, right? This angle equals to this angle. And also because OMBN is a cyclic quadrilateral, so we know that angle CNO equals to angle BMO, right? This angle equals to this one. And we know that angle AMO plus angle BMO, that's 180 degree, which means the angle CPO plus angle CNO equals to 180 degree, right? That means CPON is a cyclic quadrilateral, which means the circumcircle of the CPN, of the triangle CPN, is concurrent with other two circumcircles on this point O. Okay, that's Miguel's theorem. And now let's look at complete quadrilateral theorem. Okay, let's look at this one, the complete quadrilateral theorem. Let me adjust to this. If A, B, C, D, E, F is a complete quadrilateral, first of all, we may need to explain what is a complete quadrilateral. Complete quadrilateral is saying that we have four lines on the plane, and these four lines, there's no three lines are concurrent on the same point, right? So basically, for four lines, we would only see this case, right? That's and in that, so these four lines are on this plane, and there is no three lines concurrent on the same point, right? And then we call this as a complete quadrilateral. Okay, so this is a complete quadrilateral, and we know that ABCD meets on E. So and ADBC meets on F. So let's call A, B, C, D meets on E, and ADBC meets on F, right? Then the triangle EAD, triangle EBC, triangle FAB, triangle FDC. The circumcircle of these four triangles are concurrent, and the concurrent point is called Miguel point. Okay. Basically, it's saying we have an arbitrary complete quadrilateral, and now we want to prove that the circumcircle of triangle ECB and circumcircle of triangle EDA and circumcircle of triangle FDC and circumcircle of triangle FAB are concurrent. Okay, let's just think about the first case that we would have the circumcircle here for the triangle BCE, right? And we also have the circumcircle of triangle EDA, which has an intersection point here. Let's call it O. Right? Basically, we want to prove that this point O combined with triangle FDC, this point is C, right? I write it here. So we want to prove that FDCO is a cyclic quadrilateral, and also we want to prove that FABO is a cyclic quadrilateral, right? And what we know here is that CBEO is a cyclic quadrilateral, so we connect CO here, and we connect OE here, right? And we connect FO here. Right. So as you can see, the angle COE plus angle CBE equals to 180 degrees, right? And also we can write angle COE. This angle equals to angle let's call it ABC, right? So this angle equals to this one. And angle ABC equals to angle FDC, right? That means angle COE equals to angle FDC, which means FDCO are cyclic, right? This angle equals to this one, so it's cyclic. And we already proved that FDCO are cyclic. We want to prove that FABO are cyclic. Let's connect BO here. Right, we want to prove that this is cyclic. Basically, we know that angle BOE equals to angle CBCE equals to angle FCD equals to angle C. This one equals to this one, right? Because they are all on this circle and the circumcircle of triangle BCE. This angle equals to this angle equals to this angle. And this angle equals to angle FAB or angle DAB. Right, that means angle BOE equals to angle FAB, which means FABO are cyclic. Which means the circumcircle of triangle BCE, triangle EAD, triangle FDC, triangle FAB are concurrent on this point O. Okay. That's a complete quadrilateral theorem, and now we look at the four circles theorem. Four circles theorem is saying that let circle C1, circle C2, circle C3, circle C4 be four circles. A1 and B1 as intersection points of OC1 and OC2. Circle C1 and circle C2. So let's just draw it here. I hope you can see my drawing. But we want to prove four circles here. This one is here. This one is here. And we call this one C1, this one C2. Here is A1. Here is B1. And we call this one, this is C3, right? The intersection point A2 and B2 are the intersection point of circle C2 and circle C3, circle C2 and circle C3. So we have A2 here, B2 here, B1, B2. Okay, this is C4. Then we have A3 and B3 are the intersection points of circle C3 and C4. So this one is A3, this one is B3. And A4, B4 are the intersection points of circle C1 and circle C4. So this one is A4, this one is B4, right? Now we want to prove that A1, A2, A3, A4 are cyclic if and only if B1, B2, B3, B4 are cyclic, right? So let's assume that B1, B2, B3, B4 are cyclic. So we connect them together. Then we know that the angle B1, B2, B3 plus angle B1, B4, B3 equals to 180 degrees. Right? We know that B1, B2, B3, B4 are cyclic. We want to prove that A1, A2, A3, A4 are cyclic. Right? So we know that angle B1, B2, B3 plus angle B1, B4, B3 equals to 180 degrees. Now we can connect A1, B1, connect B2, A2, connect A1, A2. Similarly, connect A3, B3, connect A2, B3. We connect A4, B4, connect A4, A3. Right? And connect A4, A1. So we know that this angle plus this angle equals to 180 degrees. And we also know that angle B1, B2, B3 plus angle B1, B2, A2 plus angle B3, B2, A2 equals to 360. Right? So this angle, the B1, B2, B3 plus B1, B2, A2 plus B3, B2, A2, this angle. That's 360. And for this side, we know angle B1, B4, B3 plus angle B1, B4, A4 plus angle B3, B4, A4 equals to 360. Right? So this is first one, this is second one, this is third one. We use 2 plus 3 minus the first one. Then we get that angle B1, B2, A2 plus angle B3, B2, A2 plus angle B1, B4, A4 plus angle B3, B4, A4 equals to 540 degree, right? And we know that angle B1, B2, A2 plus angle B1, A1, A2 equals to 180 degree, which means we can write it as angle B1, B2, A2 plus angle B1, A1, A2. Plus, for this one, we have B3, B2, A2, B3, B2, A2 plus B3, A3, A2, right? So plus B3, B2, A2 plus angle B3, A3, A2, right? The angle B3, B2, A2 plus angle B3, A3, A2, right? That's 180 degree. So plus angle B1, B4, A4 plus B1, B4, A4. That's this angle plus this one. The angle B1, A1, A4 is 180 degree plus angle this one B3, B4, A4. B3, B4, A4 plus angle B3, A3, A4. That's 180 degree, right? That equals to 540 plus, see, the angles we added here is this one, this one, this one, and this one, right? So that's 540 plus angle B1, A1, A2 plus angle B1, A1, A4, which is angle A2, A1, A4, right? And plus angle this one, B3, A3, A2 plus B3, A3, A4. That is A2, A3, A4. Right? And we know that this is 180 degree, this is 180 degree, this is 180 degree, this is 180 degree. So that's 180 degree times 4 equals to 540, which is 180 degree times 3, plus angle A2, A1, A4, plus angle A2, A3, A4. Right? Which means these two, the summation of these two angles, that's 180 degree. So we got A1, A2, A3, A4 are cyclic. Right? And if you look at this derivation, we can reverse on every step. Which means if A1, A2, A3, A4 are cyclic, then B1, B2, B3, B4 are cyclic. Okay, that's a four-circle theorem. Now let's look at a harder one. It's called five-circle theorem. I'll just draw here. Five-circle theorem. Let A, B, C, D, E be any pentagon. So actually I'll draw it like this. That would make the let me redraw it, because this figure needs to be very careful, otherwise you would see a very huge figure here. Okay, this is better. Okay, that's A, B, C, D, E we have. A, B, C, D, E. Right? And F, G, H, I, J are the intersection point of EA and BC. So let's draw EA and BC, which means we have EA here. And we want to right, that's EA and BC has an intersection point called F, right? And G is intersection of AB and CD. So AB and CD. H is BC and DE. So BC and DE. That is H. I would be CD and AE. So J is intersection point of DE and AB. Right, that is J. Therefore, the intersection points of the circumcircles of triangle ABF, triangle BCG, triangle CDH, triangle DEI, triangle EAJ, other than the intersection point of this triangle, the intersection point of the circumcircles of these triangles, other than A, B, C, D, E, these 5 points are cyclic. What is saying is that if we draw a circumcircle of this one, and we draw a circumcircle of the triangle JAE, these two circles has two intersection points. One intersection point is A, and they have another intersection point around here, right? And the circumcircle of this one and the circumcircle of this one have two intersection points. One is point B, and there is another one, right? And the circumcircle of this one and the circumcircle of this one has a 2 point. One is point C, and there is another one here. Similarly, the circumcircle of these two triangles have two intersection points. One point is D, and there is another one here. Similarly, we have two circles here, the intersection point E and another point. And we want to prove these 5 points are cyclic. Now you can see why I said that this figure is kind of difficult to draw. So let me consider about this problem here. Let me just draw a few circumcircles so we would be more clear what we are discussing. Roughly say look like this, right? It doesn't matter really. Let me just do this to draw. So here, something like that. Probably. And I would have like this. So this point, this is a point. Let's call this point as K, okay? And this point is L. Right, so we have this here, and right, call this point KL. This point would be M. Okay, and also here, then we would have N. This is point N, and here, this point is P, right? Basically, we want to prove that K, L, and M, P, these 5 points are cyclic, right? Okay, here we must be very familiar with the concept of the complete quadrilateral theorem, right? Think about complete quadrilateral. If you look at J, G, actually, if you look at J, A, G, this point is D, right? J, A, G, C, D, well, J, A, G, D, I, E. This is a complete quadrilateral. And for this triangle here, it can be used twice, right? For both J, A, G, D, I, E, and for J, A, G, C, H, D. Right? For these two cases, the triangle JGD is a common triangle in the complete quadrilateral JAGDIE and complete quadrilateral J, actually here should be B, right? JBG CHD, right? I'm saying that triangle JGD. Triangle JGD is a common triangle in the complete quadrilateral JAGDIE and complete quadrilateral JBGCHD, right? That means we already know that triangle JAD, triangle JGD, and the triangle so we know that triangle JAD and triangle JGD, the circumcircle of these two triangles has an intersection point, which is also on the circumcircle of triangle IED and triangle IAG, right? That's from the four circle theorem, or complete lateral, actually it's from the complete quadrilateral theorem, right? Okay, and that point is this point, right? The point L, which means point L and point L is also on the circumcircle of triangle JGD. right? Similarly, the point N, we already know that point N is the intersection point of the circumcircle CHD and the circumcircle of the triangle CBG, right? That's the intersection point of these two circles. And for the complete quadrilateral JBGCHD, we know that this point is also on the circumcircle of triangle JGD, right? Which means LNG, let me rephrase, which means LDNG J. These points are cyclic, right? Are on the same circle. So the question is that we want to prove K, P, N, M, L are cyclic. So if we can prove that any 4 points are cyclic, because this figure is like you can rotate all the characters and do the same proof, right? So if we can prove any 4 points of the K, P, N, and L are cyclic, then we prove that 5 points are cyclic, right? So let's think about how can we prove that K, N, and L are cyclic. We connect them here. Right, question is that can we prove K, N, and L are cyclic? So we already know that the point N and the point L and J, G, N, D, L, these 5 points are cyclic, right? Let me write it down. J, G, N, D, L. These 5 points are cyclic. Right? That means J, N, D, L are cyclic. Right? J, N, D, L are cyclic. So if we want to prove that K, N, M, L are cyclic, we just need to prove that angle NKL, this angle, plus angle NML equals to 180 degrees, or angle KNM, this angle, plus angle KLM, this angle, to be 180 degrees, right? Actually, let me just print out this figure. It would be easier to show because here I think it's too messy. I'll put this in the next video. I hope you like this video. See you in the next one.